All right, this is part 2 of 8.5, and it's very similar to part 1. It does talk about how if we have an exponential decay system, we need to realize that the k is going to be negative, but it's because it's decreasing. I wouldn't even recommend worrying about that too much. If you put the numbers in and solve for it normally, you're going to get a negative k value anyway. So what we're going to do here is we're going to use the information they give us. It says that the half-life of polonium-210 is 140 days, and a sample of this element, and it should say probably currently has a mass of 300, but what we're going to use is the same formula we did before. So the amount we have, f as a function of time, is still going to be equal to c times e to the kt. This is going to be our c value because that's the initial amount of polonium-210 we have. So I have 300 times e to the kt. I know that in 140 days, I'm going to have half as much. So that means that basically the function f evaluated at 140 will yield half as much. So 300 divided by 2. Now I'm going to use those two together and say that 150 is equal to 300 times e to the power of kt. Sorry, that shouldn't be t, that should be 140. We know that the time elapsed is 140 days. So this is k times 140, and I'm going to solve for k. So I'm going to divide by 300. I get that 0.5 is equal to e to the power, and I'll write it as 140k, which means the natural logarithm of 0.5 is going to be equal to 140k, and when I divide that by 140, I get that the natural logarithm of 0.5 over 140 is equal to k. Now, some students don't like that because, hey, that's not a negative, but one of the things we can do is we can write the natural logarithm of 0.5 as the natural logarithm of 2 to the power of negative 1, or the negative natural logarithm of 2. And I think that does help to see that negative k value. That's a little bit of weird kind of logarithmic manipulation, but we are going to use that other form because it's a little bit more comfortable, I think, to plug in values and use in the future. So f of t, let me use a different color here. F of t will be 300 times e to the power of the negative natural log of 2 over 400 times the time. You are going to find that a lot of these exponential growth and decay functions can get a little bit ugly like that, but it is a very big benefit to be able to identify where all the values have come from. So if they want us to find the mass after 50 days, we are looking for f at 50, and that's going to be equal to 300 times e to the power of the natural log of 2, sorry, negative natural log of 2 over 140 multiplied by 50, and I get that the value of f at 50 is equal to 234, and the same unit we were given, so milligrams. All right, C wants us to find the rate of decrease after 50 days. It's actually kind of useful to know where that 234 comes in, but I'm going to focus a little more on actually taking the derivative. This question wants us to find f prime at t. Sorry, well, I'll write it like this. It wants us to find f prime at 50. Well, let me write, I'm just going to bleed in a little bit on top here. F of t was 300 times e to the power of negative natural log of 2 over 140 times t. So f prime of t is going to be 300 times e to the power of the same thing. And this does confuse students quite a bit. That it appears the derivative hasn't done anything, but we have to multiply by the derivative of the exponent, which is negative ln 2 over 140. And now when we plug 50 into that, I find that f prime at 50 is negative 1.2. Now, what that means is that it's losing negative 1.2 milligrams per day due to that radioactive decay. All right, for D, it wants us to identify how long will it take to decay to a mass of 200. This is basically solving when will 200 be equal to 300 times e to the power of negative ln 2 over 140 times t. You don't have to, write it as a fraction, but I think it is beneficial to immediately divide it by 300. And I'm going to write 200 divided by 300 as 2/3. And that's going to be equal to e to the power of negative ln 2 over 140 times t. I'm going to use that natural logarithm now, though. So the natural logarithm of 2/3 is equal to negative ln 2 over 140 times t. I'm going to multiply by 140, divide by negative ln 2, and I get that t is equal to 140 times the natural log of 2/3 divided by the negative natural log of 2. Don't get too worried about that negative natural logarithm. You won't get a negative time because the natural logarithm of 2/3 is also negative. So when we do type that into our calculator, what we get that t is equal to 82 days. All right, a couple different just exponential applications. The last thing that we're going to talk about in these notes is the idea of continuous compounding, and this is something that we've looked at before. We didn't quite give it to you in this form, and I want to identify what everything is. A is still the accumulated amount. So this is if we're getting compounds every month or week or something like that. P is the principal. I, and this is a little bit different, it's the decimal interest per compound, not per year because it's not divided by n or anything like that, compound. And then finally, n is the number of compounds. All right, if it's compounding continuous, there's no bank in the world gives us, but compounding continuously is useful if you want to predict maybe kind of best case scenarios or future values. A is still the accumulated amount. P, as you might imagine, is still the principal. And what R is the decimal annual interest rate. I spelled interest really badly. Let's try that one more time. Interest. All right, and then of course, because we're looking at annual now, T would now be in years. So two different formulas to basically deal with the same thing. But what's important, I think, to recognize, and it's why we do this question in the notes, is what we're going to look here is basically we're going to change when the compounds are. So if we get an annual compound, then the amount that we're going to have is going to be equal to $1,000 times 1 plus 0.12 to the power of 3. So that's one compound every year. And I mean, we make money, right? The bank is effectively giving us money to loan our money out. So I get 1404.93, which isn't bad, right? 400 extra bucks. But what about semi-annually? Now it's important that if it's semi-annually, I is no longer equal to 0.12. It's going to be equal to 0.12 over 2. Because we're going to get half as much interest, twice as often. So this is going to be the accumulated amount is equal to 1,000 times 1 plus 0.06. But because I'm getting a compound every half year, the exponent is going to be 6 there. And what we see happening is all of a sudden we have a little bit more money. And the reason we do is because we are getting more interest on the interest. If you look at quarterly, that's going to get a little bit better. The accumulated here is going to be 1,000 times. Erase that, it's just going to be confusing. Inside the bracket, we're going to have 1 plus 0.03. That's just 0.12 divided by 4. And we're going to have 12 compounds in the space of 3 years. And I get that the accumulator is even higher. It's 1425.76. Now, we're not talking about a great deal higher, but we're not talking about a lot of money either. Right? Try to picture imagine investing $10,000. And then the difference in these is more significant as we go. For monthly, if we get 12% a year, I get 1% a month. So the accumulator will be 1,000 times 1 plus 0.01, but now it's to the power of 36. So even though I'm getting less interest, I'm having more compounds, and it does end up making me just a little bit, but more money. Now, what happens when it's continuous? As soon as it's continuous, I can't use the formulas I have above. I have to use that A is equal to 1,000 times e to the power of 0.12, and then there's 3 years there. Now, compounding continuous means that it's continuously compounding. And that does mean that the interest rate tends to 0, but we get so many compounds, and it turns out that this is the most money that we can make. And that does make sense, right? The more compounds you get, the more money you're going to have, because you're getting interest on the interest on the interest. No bank in the world, doesn't know that. And so I have never seen any bank that offers continuous compounds, because again, they would be losing out on money. They'd have to give us more money. All right, that's it for 8.5. Make sure you try these questions. I know there's a lot of them, but it's really important we get comfortable in manipulating and modeling real situations using this math.